Okay, so let us proceed from where we left last time. We were discussing some basic issues in real time communication, but before we proceed further in the real time communication, I thought it may be a good idea to review some basic issues in computer networking, so that those who already know this will refresh their knowledge, and those who did not know much about computer networking, they can be on a footing where they can cope up with the discussions that we have in the subsequent hours. So, let us proceed from there. We will spend an hour to review some computer networking issues, which will appear again and again in our discussions later on. So, CSMSCD is a multiple access protocol. We will not spend time, because requirement for this course was a basic course on computer networking. So, this is the medium access protocol. Node senses the channel status, and if the channel is found to be idle, then the transmission begins. When multiple nodes attempt to transmit at the same time, collisions occur. But one thing that we must understand is that the larger the propagation delay of a network, the larger is the probability of collision of packets. Do you agree with this? So, why is that?
Holding the channel for longer time.
What do you mean by holding the channel? See, what we are saying is, larger is the propagation delay. We had discussed about propagation delay, the time the signal, the time it takes for a signal to propagate or travel from one end to the other end, or from the point where the node is attached to both the ends, right? The time it takes.
For a long time period, the channel portion of the channel will be reserved by that frame or packet.
No, sorry.
Large propagation delay, transmission from other stations can initiate.
Can you please repeat again?
Due to large propagation.
Large propagation, yes.
Same transmission time for other stations.
Yes.
Can be initiated within that period. As the frame transmission is compared to less than the.
Okay, let us hear if somebody else is telling anything. So, what is your opinion? Why is it that the larger is the propagation time, the more is the chances of collision?
So that's what this. If it is the channel is being held by being used by one station,
yes,
then in between the other stations,
The probability that another station transmits is more.
not clear. It is not that complicated. See, the answer is that, see, a station transmits after sensing the channel to be idle, right. So, it may so happen that it has sensed the channel to be idle, but by that time some other station had already started transmitting, and it is taking time for it to reach here, right. So, the more is the propagation distance, the more is that difference where the other stations could initiate the communication, but other channel will not be able to detect it. It sends the channel, it is idle, but by that time actually somebody had started transmitting. See the problem?
Yes, sensing will be that wherever the packet is on the LAN, if it is far also it can sense.
No, it cannot. See, the signal takes time to travel, just remember that. Maybe for a large, if we consider a very large network, it may be millisecond, right. So, in that millisecond, some station has already started transmitting signal on the line, it is sensing the line, finding nothing is there, the signal has started from there, has not reached here. See the problem. So, the larger is the length of the channel, length of the medium, the more is the probability of the collision, and the more will be the degradation of the performance, and that is one of the reason. There are many reasons from a first level course you will see. One of the reason, the length of the LAN is restricted by this, the propagation time. There are many other factors you will find in a, let us not spend time on that. because we have many issues to discuss. And once a node detects collision, I mean, see, this is the reason why collisions occur also. See, the reason we are saying that it takes time for the signal to travel, and that is why collisions occur actually, because it will be extremely rare that two sources exactly transmit on the same time, same instant of the time, because once a signal is transmitted, the channel, if it is found to be occupied, it is busy, then the others will not transmit, is not it. So, where is the chance of a collision? Let us assume that two stations do not generate or do not really start to transmit exactly on the same time in the clock sense, that same, let us say, nanosecond, if we are talking of a gigabit Ethernet, let us say in the same nanosecond precision they do not transmit. So, will collisions occur or no? Still collisions will occur because of this transmission delay. Is that okay? And from the first level course, you would know that the CSMACD does not define a collision resolution protocol on its own. There are different implementations possible. For example, Ethernet uses something, and for example, CAN uses something. Ethernet is a popular implementation of the CSMACD protocol. It's very popular due to simplicity, low cost, high speed. All of you know very well Ethernet from a first level networking course. Uses the binary exponential backup algorithm for collision resolution. And since it is such a popular network, present everywhere, every lab, every office, it is there, and because of the uses to such a large number, the cost also has reduced considerably because of the sheer volume of the demand on Ethernet. It is very inexpensive. Even as a hostel room, you can set up a Ethernet in few hundred rupees. So, naturally, people are interested to use Ethernet in real time application, but the basic problem here is that does not distinguish between stations, all are treated equal. We will see some attempts that have been made to extend Ethernet to support real time communication, and they are successful to various extents, but in some applications can be used. We will discuss this about 2 hours or so later. The data link layer is actually consists of two sublayers, the logical link control and the MAC sublayer, which we know from the first level course. The medium access control, it implements the arbitration mechanism, right, which node will be allowed to transmit, that is inbuilt into the MAC protocol. So, the MAC layer, it decides, the MAC layer is the one which decides for how long a node can transmit and when it will be able to transmit. It is very important for a real time application, because precisely we have to tinker here, we will have to manipulate this in a real time protocol. We are saying that Ethernet is being also used for real time applications. So, to adapt Ethernet to real time application, we will exactly have to somehow control this, when exactly a node will be able to transmit, which node will be able to transmit, and for what period, I mean how long it can transmit. Based on that, we can deterministically say that when other data can be transmitted by the other nodes, right, because we need that all real time data should be transmitted in the required time. So, there are two policies inbuilt into the MAC layer. One is about when somebody can transmit, the other is how long. When is decided by the access arbitration protocol. The access arbitration is when multiple nodes start to transmit. It decides, the access arbitration protocol decides who is eligible to transmit, the others should back off. The transmission control policy on the other hand decides for how long the transmission can occur. Once a node is allowed to transmit, for how long can it occur? It cannot just monopolize and then all other nodes will miss out on their deadlines. So, these policies together, the access arbitration and the transmission control policies together, they form the medium access control layer, the MAC layer protocol. Several times as we proceed, we will fall back to this. We will be talking of the MAC protocol, the access arbitration protocol, transmission control protocol. I hope by that time you will be able to recollect this. Okay, this we had already discussed, that the MAC layer, one of the work is to determine which node accesses the medium next. And typically when you talk of a LAN, you talk of in terms of the MAC protocol it implements. For example, if somebody asks that what kind of network you have in the lab, I mean in older times, now we do not have this in the lab, you will say that we have a 10 base T Ethernet. So, that is the MAC protocol. The 10 base T Ethernet is one type of Ethernet, right. That is, its MAC layer protocol is 10 base T Ethernet.
What is meant by 10 base?
Yeah, we will just discuss about this 10 base T, because such names we will hear, and you will also hear somebody will ask you what kind of network you have in the lab. So, we will discuss this term. But how does a workstation get its data onto the LAN medium? The MAC protocol is the one which decides which node workstation would transmit the data, and then the turns are defined and they take turns in transmitting data, and based on what kind of protocol is used for the different stations to take turns in transmitting, either we have a contention based protocol or we have a round robin protocol. So, these also you know from a basic course on networking, we are just refreshing those, because we will use both these types of protocols in real time application. We will have real time protocols defined on the contention based protocols and real time protocols extended round robin protocols. If you see the last 20-25 years that the Ethernet is in existence, there are several types of Ethernet that have come in: 10 base 2, 10 base 5, 10 base T, 10 base F, 100 base T or the first Ethernet, 1000 base T or the gigabit Ethernet, which we have in the lab now. Let us see what do these mean: 10 base 2, 10 base 5, 10 base T, 10 base F, 100 base T, 1000 base T, etc. What do they mean? The numbers and so on. The 10 base 2 existed quite some time back, maybe 15-20 years back. Those days it was called as the thin Ethernet. Nowadays nobody uses this, but old networks you can still find them. It operates at 10 Mbps, 10 Mbps, and the maximum distance of this network is 200 meters. So, uses a thin coaxial cable in bus topology. We had seen the bus topology, the BNC T junctions and so on. used to be like this: the coax cable, the 10 stands for 10 Mbps, 2 for 200 meters, and base for baseband transmission. I hope all of you know what is a baseband transmission, how does it differ from a broadband transmission. So, the LAN transmissions occur at baseband. So, the nodes are connected through an adapter, which is a LAN card, a LAN adapter, to the bus, which is a coax cable, thin coax, and T junctions terminated, but multiple segments, LAN segments, can be interconnected using repeaters or hubs. A hub would transmit every bit appearing on the bus to the other bus. And then we had the 10 base 5, it was called as the thick Ethernet, used a different type of cable, and the transmission distance was 500 meters. But one of the reason we were saying is that as the distance, I mean the length of a LAN increases, the collisions become more and more. The probability of collision increases, right? But other than that, what restricts the length? I mean, we saw a 200, a thin Ethernet is 200 meters, and a thick Ethernet we are saying 500 meters. What restricts the distance? See, this also the transmission is 10 Mbps.
Because this is using a thick cable, so that is a thinner coax cable.
So, how does that matter?
That will
I mean, what difference does it make, whether it is a thin cable or a thick cable?
the drop across the line will be more in that case than this one.
Okay.
So,
Okay. Okay. Signal attenuation, that is a major problem that restricts the length of a LAN segment. So, that is what he says, that in attenuation will be more in a thin coax cable compared to a thick coax cable, and that is the main reason why this one is 500 meters, the other one is 200 meters. But again, when the cable is too thick, you can't, it is very difficult to use, right. So, the thick Ethernet was rarely used in lab situation. It was used as a backbone. In the lab situation, it was the thin Ethernet which was popular. The thick Ethernet was used as the backbone to connect different LAN segments. The thick cables were inflexible and not really suited to interconnect a computer. No, how do you, a thick cable, how do you attach to your computer? You can't really bend it and so on. Whereas a thinner cable is much more easier to interconnect. So, the LANs used to be thin Ethernet, and then the interconnection between the LANs used to be thick Ethernet. And then we had the 10 base T. About 15 years back, the 10 base 2 and 10 base 5 were completely abandoned. Suddenly the 10 base T became popular, it suddenly vanished actually, the coax cable. Within a year you find that nobody is using a coax. Here T stands for twisted pair. Why do twist the wires?
reduce the noise electrical interference.
I mean, how does that reduce the electrical interference?
If you twist it, there is a noise on one of the twisting.
Okay.
It will be on the both the things, so that
Okay.
will cancel out.
Okay, okay, yeah, exactly. So, if they are tightly twisted, then similar noise will be induced on both the wire, and when the signal, the common mode, I mean the common mode noise can be eliminated and the signal can be will not be affected by the noise. Yes, that is the idea. And then the Cat3 and Cat5 were used for 10 base T in the subsequent years, first Cat3 and Cat5. What is the difference between a Cat3 and a Cat5 wire? Cat basically a category, isn't it? Category 3 and category 5. Cat 5 has more turns per square centimeter per centimeter, tightly twisted. That is one thing, but then we will see that the number of wires inside is also different. Number of strands, that is also difference. So, some type of network you can implement at Cat 5, which you cannot, those protocols you cannot implement on Cat 3, because the wires are different. We will just see that. The twisted pair suddenly became popular because it reduced cost and at the same time increased reliability, became a star connection in no time. I mean, 1 year you find that the labs are set up using a bus, next year you see those are obsolete, use a star connection to set up your lab and use twisted pair and at much reduced cost. So, and not only that, very increased reliability. One wire has problem, still the network operates, only one computer is not working, change the wire, it will work. Deviates substantially from the base 2, 10 base 2 and 10 base 5 topology, became a star topology from a bus topology, sudden change in the topology, and the nodes were connected to a hub. So, to the hub, the connections from different computers were attached and it appeared something like this. If this is the hub, then the computers were all attached to it, form of a star network. If we compare this different network, the 10 base F was based on fiber. Naturally, the distance of the network is larger and the number of nodes that can be attached to it is also larger, because each node syncs some signal, isn't it, as it listens to the noise, listens to the signal, it syncs some signal from it. Naturally, 10 base F will have many more stations attached to it, typically used between buildings, inflexible. 10 base T, also you can attach large number of nodes, e.g. maintenance. And then we had the fast Ethernet, which appeared around I think 8-10 years back. The computers became faster, internet had come in and there was need for letting the computers operate and transmit at a faster rate. But how can somebody transmit at a faster rate on the same twisted pair? It's again a twisted pair, the kind of noise, etc. See, basically the signal rate is restricted on how much noise is getting induced, isn't it? As the signal rate increases, becomes gigabits and so on, little bit of noise also can create problem, right. So, it is the same twisted pair. So, how is it that able to transmit at 10 times the speed? The reason is that a different encoding was used in the 100 Mbps network. The 100 base T used the NRZI encoding compared to the Manchester encoding, the older encoding in the 10 Mbps. So, the data transfers could occur at a faster rate without substantially increasing the quality of the medium or the signaling speed of the medium, without substantially making difference to the medium, could transmit at a faster rate because of a different encoding used to transmit the signal, where it is more noise proof.
What does it I stand for?
Non return to 0, I do not know, you have to look up.
That is
Inverse,
inverse.
okay, it is name of a encoding scheme. You can find it in any book or just search on the internet, you will find that. And then we have the gigabit Ethernet now present in the labs. There are two different versions, one using the twisted pair, another using the fiber. The gigabit Ethernet is also referred to as 1000 base T. All these Ethernet transmissions are baseband transmissions, just remember that. Requires a Cat5 cable. We will see why Cat5 cable. 100 meters only, uses a 5 level pulse amplitude modulation. So, again the modulation changed. And that is partly the reason why signals could be transmitted at a faster rate. And now we have 10 gigabit Ethernets are available. So, these cards take care of transmitting gigabit and can be attached to the gigabit network. Okay, I think the answer is to, we are just trying to answer some question, isn't it? What was it? I mean, how it could become gigabit Ethernet without, and why does it run on Cat5 alone, right? Why not on Cat3, a gigabit Ethernet? Okay. So, we do not have the answer right now here on the slides, but the answer is something to do with the protocol and the full duplex transmission that became possible. The full duplex transmission, we will just see it shortly, and at the same time a station can both receive and transmit. It is restricted to only receiving or transmitting. We will just look at that issue now, I mean shortly afterwards, and two pairs of wires were needed for the protocol. Okay, naturally when you have full duplex communication, you need two pairs of wires, isn't it? So, we will just see that exactly. So, we will just look at that, but since we will be discussing later quite widely on LAN interconnections in real time communication, we will also answer a few basic questions, address basic issues in LAN interconnection. One question is that why not just have a big LAN? What is the advantage of first level knowledge, actually first level networking knowledge, that why not have one big LAN? Why do you have one LAN in one lab? No, we have some 3-4 labs in the department, separate LANs there and then interconnect them. Why not all of them in the same LAN? Why not cost effective?
Because if you have to connect the whole thing with the same type of
You mean cabling cost? Cabling cost? No, cabling cost is not much. Twisted pairs anyway do not cost much. How it is reliable? I mean, how by making it?
A link is broken, the
Yes.
entire network will fail if we use a big LAN.
No, in a present day star connection, it one link broken does not bring the network down. Sorry.
It's a complex physical structure.
Why complex physical structure? You can
Then you have to spread cables of different lengths.
Cables of different lengths doesn't matter, you can always attach cables of different length.
If you have modularized structure, small LAN, then it's easy to debug any failure will occur.
No, that's what he said, no, link fails. But I was saying that link fail doesn't bring the network down. You know a link failed and you just replace that link. Why is it to debug? There also, see, when you have a large LAN, found that computer is not working, you know that something wrong with the link. Here also same thing, when there are multiple LANs, found one computer not working, look at the link, because they are star connection, just remember they are not bus connections. Okay, no, not really. So, let us see the reasons why we need to separate a large lab into smaller LANs. One is that in a single LAN, all stations share bandwidth. If you put 100 of them, the chances of collisions will be too much, and the throughput will reduce drastically, because they are in a broadcast mode, and any node can disrupt traffic from another node, right? They contend for the same channel, and every LAN supports a limited amount of traffic. So, this is one major reason that when you separate them into interconnected LANs, it becomes much more easier for computers to communicate without a performance degradation. Second reason is the length restriction on the LAN. A single LAN, we were just mentioning that there are several reasons why the length is restricted, the cable length is restricted. Large collision domain. So, these 2 points, the first point and the third point are slightly different. The first point says that if each LAN supports, let us say 10 Mbps or 100 Mbps, then 5 of them will support 500 Mbps traffic at the same time, whereas if it is just one large LAN, at best it can support 100 Mbps. The collision domain in a large LAN, the collision domain is large and any node can collide with any other node. Here you are restricting the nodes with which it can contend. And not only that, the different LAN protocols, they limit the number of stations that can be attached, and also in the token ring architecture, you have delays at each station that occurs. So, it becomes, if you have too many stations in a token bus or a token ring, then by the time a station gets its turn, it may be too late for a real time application. So, this we know that we have network of networks, small I internet and capital I internet. We know that the difference, is not it? Small I internet is any two connection of networks, whereas if it is a capital I internet denotes one specific instance of the internet. See, if we have one LAN here and another LAN in the other room, you can just interconnect them and we have a small I internet, but the capital I internet denotes to one specific network on which the World Wide Web is hosted, right. And then the parts are the sub networks. Various devices are used to interconnect the networks, hubs, switches, bridges, you know them, the routers. Will not spend time on that. We can say that capital I internet is an example of a small I internet or is a specific case of a small I internet. We will just spend a couple of minutes in reviewing the internetworking. So, this is a typical situation where we have interconnected some LANs using a router or a switch. We have hubs and interconnected them using a switch. Hubs, we know that these are physical layer devices, repeat every bit, operate at the bit level. They do not understand addresses, etc. Just whatever bit they appears on the line, they repeat it in all interfaces. Available, as we were saying, very inexpensive, few hundred rupees can find in the market. Arranged, this can be arranged in a hierarchy with a backbone hub at the top, can be configured like this. You have different labs here, adjacent labs, in each one has a hub and then interconnected in a tree configuration with a hub at the root. So, here the need for the host to detect a collision limits the size to 5 hubs per 10 Mbps Ethernet and 3 hubs per 100 Mbps Ethernet. Do you agree with this? That for a 10 Mbps Ethernet, you can have 5 hubs interconnected in a tree hierarchy. For 100 Mbps Ethernet, you have 3 hubs. Why is that? And the answer we said is that to be able to detect a collision. Do you agree with this? See here, 5 for 10 Mbps and 3 hubs for 100 Mbps, that can be interconnected. In a tree actually. So, why is that? So, this is the size of the hierarchy or the depth of the hierarchy. I am not saying the total number in the hierarchy, sorry, total number of hubs that can be interchanged. The one that we are saying size is actually the depth of the tree. Exactly, yeah, that is based on what we discussed few minutes back, is about the propagation time, because each LAN we know that it is 100 meters, right. So, if 5 of them are there, the depth is 5. So, the transmission from one to the other extreme will be 1000, is not it, 5 and 5. So, for that it is 1000 meter it becomes, right. So, at a lower signaling rate 10 Mbps can still manage with 5, but as the signaling rate becomes higher, it is too much, 10 hubs is too much. So, again the answer is based on what we discussed couple of minutes back, the propagation delay and how is the collision can occur. The chances of collision is more if the length of the medium is more, etc. The answer is in the same thing here, right. Is that okay? Okay. But one problem with such a tree of hubs is that they do not isolate collision domains. The transmission from any node can collide with transmission from any other node in the hierarchy. So, as the depth becomes more and more computers get attached, there will be a performance degradation. But simple, as we are saying, couple of hundred, graceful degradation, some part gone, still does not matter, it will work. Portions of the LAN continue to work even if one hub malfunctions. Many advantages are there. it is more robust than the coax cable, and not only that, in a coaxial cable, if you have a malicious host, I mean not malicious, may not be malicious, suppose its card has gone bad, right, the LAN card has gone bad, it is just outputting noise or some junk signal onto the cable. So, that will make this fail. A coax cable will fail if one LAN card malfunctions, keeps on transmitting junk onto the bus. But in a hub situation, the hub detects which node is misbehaving, excessive collision from some hub, it can disconnect it. So, that way it is also more robust compared to a coaxial cable. But again the problem is single collision domain. Even if you have several hubs attached in a tree, no increase in throughput, and multi-tier throughput is the same as a single segment throughput, right? You agree with this, isn't it? Because the collision domain is the same. So, if it is a 10 Mbps LAN, then even if you have a multi-tier arrangement, still the traffic supportable is 10 Mbps, right. So, the geographical coverage is less and so on, and not only that, the hub cannot connect different types of LANs. For example, a hub cannot connect a 10 base T with a 100 base T, because it is after all a repeater, isn't it? Whatever it gets on one port, it will repeat on the other port. So, if it gets a 100 base T bit, it will repeat here also for this, the other segment, and this will make no sense for a 10 base T. So, these are some of the limitation of the hub, and then we had the bridges. Layer 2 device, unlike the hubs which were physical layer devices, right, just bit level they operated, but here they can examine the header, the physical address, and selectively forward frames, and they can, important thing is they could isolate the collision domains, right, because based on the physical address they can either transmit or not transmit, either repeat or not repeat. And not only that, the buffered frames, I do not know whether you have seen a bridge or some, you have seen a bridge or no. Have you seen a bridge? How does that appear? Okay, typically they are implemented using a computer, because they need to do several things like buffering frames and so on, typically implemented in a software. Isolates collision domains, higher throughput, relaxes limit on the number of nodes and maximum length, can connect different types of Ethernet, because it stores, it buffers them, right. So, even if it does not just transmit, once a bit comes, it need not just read out the bit without waiting for the next bit. Here it buffers them, and a 10 Mbps signal, a 10 Mbps LAN, it can read out at 100 Mbps, or a 100 Mbps it can transmit on one port, where a 10 Mbps Ethernet is attached, right. So, it can interconnect different types of LANs. It does not just repeat the bits, it buffers the data. It is a store and forward device, first stores, and that is the reason why it can interconnect different types of networks. And also it is transparent, you do not have to change the LAN adapters, it works with the same LAN adapters, you do not know whether you are attached to a hub or a bridge. And the next development was a switch called as the Etherswitch. a development on the bridge. The bridge examined each packet one by one, as we were saying that it had a CPU, many times looked like a traditional computer, a PC or something, and it examined, it stored the packets, and there was a software, it was software driven, examined each packet, and as a result, because it was a software implementation, the bridge was a software implementation, it stored the packets, then transmitted. It performed even worse than the hubs. 1989, networking company Kalpana Networks, must be there many Indians in this company who gave the name Kalpana Networks, introduced the first switch, Etherswitch. The idea was that there are several innovations actually. One is that it does bridging in hardware. All these are implemented in hardware, the examination of the header and so on, forwarding. It could forward packets at a faster rate compared to a bridge, which was a software implementation. The switch was a hardware implementation, and also it used multiple ports. It could handle simultaneous connections at the same time. In a bridge, at best one connection can occur, right? One computer can talk to another computer, but here using the switch there are multiple ports and each pair of the ports can talk to each other. Multiple simultaneous interconnections can occur. So, there are several innovations, and then the manufacturers are given the name switch. It did not appear in the standard. Later, of course, it became so popular, the name had stuck. People referred to it as switch. It's improvement over the bridge. And when the frames are received on any port, the MAC address or the physical address is read and the frame is switched to the specific port. This is also, the bridge was doing this, it was doing it in software. Here it checks between multiple ports, the connections, the data that is coming on different ports. It checks on hardware, the MAC addresses or the physical address, and then it switches the frame to the port where it is required. And of course, how does it learn which address on which side of the port, etc. The learning thing, it is there on the bridge, etc. We will not discuss about that, not spend time on that, because it is not crucial to our further discussions. You can, those who do not know about that, please read a networking book. Multiple simultaneous conversations can occur, that is what we are saying, compared to a bridge which supported only a single connection. Here multiple conversations could occur, and there was a big improvement in the performance of an interconnection. And not only that, it buffers the frame when the port becomes available. If that same port, it wants a connection to a port which is already busy, it buffers the data. Significant performance benefits were noticed just by changing a hub or a bridge with a switch. And also the full duplex communication became a reality. At the same time, data can be received and also transmitted. And another improvement over the bridge is that it was a completely store and forward. A frame is received, stored, header examined and then transmitted, and there is a time involved, isn't it? You receive the entire frame, examine and then start transmitting. But here it is a cut through arrangement, where as soon as it finds the header, it starts forwarding, called as the cut through. A switch forwards immediately after reading the address. But of course, there is a problem with this. The problem is that it would also forward corrupted packets, corrupted frames, because to check whether it is corrupted, need to store it fully, isn't it? So, cut throw has a problem which was later overcome. We will not discuss about that. Allows simultaneous transmission and reception of data. It helps eliminate collisions, because as long as they are connected to the switch, multiple simultaneous conversations can occur. And not only that, it is a full duplex switch, and naturally needed 2 pairs of wires to be connected to transmit the receive and send signals, but Cat5 has 2 pairs of wires anyway. So, using Cat5 you can easily set up, connect it to a switch, but might hear this term very frequently, that somebody says we use a layer 2 switch and somebody says we use a layer 3 switch. The same switch, right? What is this layer 2 and layer 3 switching? Anybody knows? 2 types of switch you will find in the market, layer 2 switches and layer 3 switches. What are those, and what are, I mean, what difference does it make whether it is a layer 2 switch or a layer 3 switch? Okay, not very difficult to answer. So, the layer 2 switches are essentially high speed bridges, the layer 2 switches. The bridges, you know, they examine the MAC address or the physical address, and the layer 2 switches are also operate on the layer 2 address, which is the MAC or the physical address. And like the conventional bridges, the layer 2 switches have scalability problems because of their bondage to the MAC address, because you know the MAC address does not have much information in that. So, if you know the MAC address of a host, you do not know, it can be anywhere in the network, isn't it? It does not have much information encoded, excepting that 2 MAC addresses are unique, it encodes no other information. But if it is the IP address, it also indicates where it will be located, and you can reduce the, you can direct it to appropriate place. You do not have to do a MAC broadcast to find out where it is located, right. So, that is the main advantage here. The layer 2 switches periodically generate MAC layer broadcasts. Whenever they do not know, they have not learned the port to which a host is attached, they will do a MAC layer broadcast to find out where it is, and very frequently they do the MAC layer broadcast and result in a high network load. You can find layer 3 switches nowadays, which direct the transmission depending on what they interpret, where the receiver, where it is likely to be located, they will transmit it on that port. Even they do not know that it is where it is, but just by examining the destination, the IP address, they will know which port it is located, and they will restrict the broadcast to that port only. So, based on the IP address, they do the ARP or the address resolution protocol, where they broadcast and find out which is the host. They do the ARP broadcasts only on the specific port, rather than doing a full broadcast on the network. And layer 3 switching naturally is more efficient. Combining the switches and hubs is a common occurrence in today's LANs. You go to our lab or anywhere, you will find that there are hubs as well as there are switches. So, which one do you connect where? Can you directly connect some devices to the switch, some computers, and some to the hub, it's a design decision actually. We will just spend a minute or two in the next discussion, because again this is important as per our later discussions are concerned about the hubs and the switches and how we will interconnect, the design decision on this. So, we will just stop here today. We will continue from this point. We will spend a few minutes on integrating switches and hubs, and we will continue from this point onwards. Okay, thank you.